1 light year. It sounds manageable. One single unit of cosmic distance. But here is what nobody tells you. 1 light year is approximately 9.5 trillion kilometers. If you launched a spacecraft at the same speed as our fastest interstellar probe and aimed it directly toward a point 1 light year away, it would arrive in roughly 18,000 years. And that is the optimistic estimate. The energy required to push even a modest spacecraft to just 10% of light speed exceeds the total energy output of every power plant on Earth, running simultaneously for decades. This is not a story about reaching another star. This is a story about 1 unit of distance that exposes the most brutal limits of physics itself. 1 light year is the wall that separates dreaming civilizations from spacefaring ones. If you enjoy journeys that completely reshape how you see the universe, do me a favor and hit that like button and subscribe. It genuinely helps this channel keep making content like this, and I appreciate every single one of you. Now, settle in and get yourself comfortable. Let's begin. Astronomers throw around the term light year so casually that it has lost its terror. Textbooks define it in a single sentence and move on, as though the concept requires no further examination. Science documentaries use it as a stepping stone to more impressive numbers. Millions of light years, billions of light years, treating the single light year as a rounding error on the way to grander scales. This is a catastrophic mistake. Because 1 light year, stripped of its casual usage and examined on its own terms, is already a distance so extreme that it exposes the fundamental helplessness of human engineering. It is not a small unit. It is not a convenient starting point. It is a wall, and understanding why that wall exists requires slowing down, abandoning every comfortable assumption about distance, and truly confronting what this single unit of measurement contains. A light year is the distance that light travels through a vacuum in 1 Julian year. Light moves at exactly 299,792.45, 8 kilometers per second. That is not an estimate. That is a defined constant of physics, one of the few numbers in science that carries no uncertainty. In 1 second, a beam of light crosses a distance roughly equivalent to circling Earth's equator 7.5 times. In 1 minute, light travels just under 18 million kilometers. In 1 hour, it covers approximately 1.08 billion kilometers. In a single day, light races across roughly 26 billion kilometers. Already, these numbers have drifted beyond anything that human beings encounter in ordinary experience. But a light year is not 1 day of photon flight. It is 365 1/4 days, 8,760 consecutive hours of movement at the absolute maximum velocity permitted by the structure of the universe. When you complete the calculation, 1 light year equals approximately 9.461 trillion kilometers. Written without abbreviation, that is 9,461 billion kilometers. For those who prefer miles, 1 light year spans roughly 5.879 trillion miles. These figures are so large that they stop functioning as meaningful quantities inside the human brain. They become strings of digits, abstract and weightless, carrying no more emotional impact than a phone number. The human mind evolved to judge distances it could walk, throw a spear across, or spot a predator within. Trillions of anything fall so far outside that evolutionary framework that the numbers become invisible. You read them, acknowledge them, and immediately forget their actual magnitude. So let us abandon the raw numbers and try to make this distance feel real. Consider the Earth and the Moon. The average distance between them is approximately 384,400 kilometers. This is the farthest any human being has ever traveled from home. The Apollo astronauts crossed it in roughly 3 days, and when they looked back, Earth already appeared small enough to cover with an outstretched thumb. 1 light year contains approximately 24.6 million of those Earth-Moon distances laid end to end. If you replayed the entire Apollo transit launch, coast, lunar arrival 24.6 million consecutive times, stacking each 3-day journey one after the other, you would finally bridge a single light year. The total travel time for that hypothetical relay, even at Apollo speeds, would exceed 200,000 years. Now consider the astronomical unit, the standard yardstick of our solar system. 1 astronomical unit equals the average distance from Earth to the Sun, approximately 149.6 million kilometers. This is the distance that defines our planet's orbit, the radius of the circle we trace around our star every year. 1 light year contains approximately 63,241 astronomical units. The entire span from the Sun to Pluto at its average orbital distance measures roughly 39.5 astronomical units. 1 light year could swallow more than 1,600 copies of the Sun to Pluto distance, placed end to end like beads on a wire. Our solar system, that vast arena containing 8 planets, hundreds of moons, a belt of asteroids, and a cloud of comets, is a speck of dust compared with 1 light year. Perhaps the most visceral way to comprehend this distance is to imagine shrinking the entire solar system down to something you can hold. Picture the Sun as a marble, roughly 1 centimeter in diameter. At that scale, Earth would be a microscopic grain of dust orbiting about 1 meter away. Jupiter would be a tiny peppercorn, 5.2 meters from the marble Sun. Neptune, the most distant major planet, would sit 30 meters out, about the length of a basketball court. Now ask how far 1 light year extends at this scale. The answer is approximately 68 kilometers. Your marble Sun sits on a table in front of you, and 1 light year away, at the same scale, lies a point farther than the distance from central London to the English coast. Between your marble and that distant point, there is nothing. No other marbles, no peppercorns, no grains of dust. Just 250 kilometers of pure, featureless emptiness. That emptiness is not merely a visual absence. It is a physical reality with consequences that ripple through every aspect of interstellar travel. The space between stars is the most thorough vacuum accessible to nature. In the interstellar medium, matter density drops to roughly 1 atom per cubic centimeter. To appreciate how empty that is, consider that the air surrounding you right now contains approximately 25 billion trillion molecules per cubic centimeter. The interstellar void is roughly 25 quintillion times less dense than the atmosphere you are breathing. If you sealed a room and removed air molecules one by one until it matched interstellar density, you would need to eliminate every molecule in the room, and then keep going, emptying building after building, city after city, until your depleted zone spanned a volume larger than a small country. Occasionally, a stray hydrogen atom drifts through this void. Rarely, an interstellar dust grain, a particle smaller than a bacterium, composed of silicates or carbon compounds, tumbles through the darkness. These grains are the detritus of ancient stellar explosions, the ashes of dead suns scattered across light years of vacuum. They are vanishingly rare. A spacecraft traversing interstellar space might encounter one such grain every few days, or every few weeks, depending on the local density of the medium. Otherwise, there is nothing. No fuel to harvest. No gravitational waypoints to exploit. No landmarks to confirm your position. The void between stars offers no assistance of any kind to anything attempting to cross it. This absolute emptiness has practical consequences that are rarely discussed outside engineering circles. Every space mission ever flown has relied, to some degree, on the environment through which it travels. Orbital missions use atmospheric drag for aerobraking. Interplanetary missions use the gravity of planets and moons for trajectory adjustments. Even deep space probes like Voyager exploited the specific alignment of outer planets to gain speed through gravitational slingshots. Remove all of that. Strip away every planet, every moon, every gravitational body between your departure point and your destination. Replace it with 9.46 trillion kilometers of vacuum containing roughly 1 atom per cubic centimeter. That is the environment a light year presents. And it means that every joule of energy, every gram of fuel, every component required for the journey must be carried from the starting line or supplied remotely. There are no rest stops in interstellar space. To feel how 1 light-year compares with the distances humanity has actually crossed, look at our most distant emissary. Voyager 1 launched on September 5, 1977, aboard a Titan IIIe Centaur rocket. It flew past Jupiter in 1979, past Saturn in 1980, and has been coasting outward through interstellar space ever since. As of recent tracking, Voyager 1 sits approximately 163 astronomical units from the Sun, roughly 24.4 billion kilometers from Earth. It has been flying for over 47 years. In that time, it has crossed approximately 0.0027 light-years. That is 27 ten-thousandths of a single light-year, less than 0.3% of the distance this video is about. Sit with that for a moment. Humanity's single greatest achievement in terms of raw distance, a spacecraft launched nearly half a century ago, boosted by the combined gravitational pull of 2 gas giant planets, now farther from Earth than any other human-made object, has covered less than 0.3% of 1 light-year. If Voyager 1 had been aimed at a 0.1 light-year distant on the day it launched, and if it could somehow maintain its current velocity of approximately 17 kilometers per second indefinitely, it would arrive in roughly 17,600 years. That is longer than the span from the end of the last ice age to the present day. Every civilization that has risen and fallen in recorded human history, every empire, every dark age, every renaissance, every industrial revolution, all of it fits comfortably within Voyager's 1 light-year travel time, with millennia to spare. The New Horizons spacecraft, which delivered the first close-up images of Pluto in 2015, travels at approximately 14.5 kilometers per second. Its 1 light-year transit time stretches to roughly 20,700 years. The Parker Solar Probe, which reaches the highest heliocentric velocity of any human-built object at approximately 176 kilometers per second during close solar passes, would still require about 1,700 years to cover 1 light-year at that peak speed. And even this figure is misleading, because the Parker Solar Probe achieves that speed only during its closest approach to the Sun. In open interstellar space, without the Sun's gravitational acceleration, it would be travelling far slower. The pattern is unmistakable. Whether you choose the fastest probe, the farthest probe, or any other spacecraft in humanity's catalogue, the result is the same. Travel times measured in thousands to tens of thousands of years for a single light-year. These are not engineering failures. These are the direct, inescapable consequences of the velocities achievable by the propulsion systems we currently possess. Chemical rockets, ion drives, gravitational slingshots, all of them operate in a velocity regime that is vanishingly small compared with the speed of light. And because 1 light-year is defined by the speed of light, any technology operating at a tiny fraction of that speed must accept journey times that are correspondingly enormous. There is another dimension to 1 light-year that rarely receives the attention it deserves. The name itself carries a clue. Light-year. It is not merely a distance. It is a distance defined by time. When you observe an object 1 light-year away, you see it as it existed 1 year in the past. The photons entering your telescope or your eye departed that object 12 months before they reached you. At interstellar scales, this means that all observation is a form of looking backward through history. You never see the present state of anything beyond your immediate cosmic neighborhood. You see the past, always, and the depth of that past grows linearly with distance. For a spacecraft crossing 1 light-year, this light travel delay becomes a profound operational constraint. Imagine a probe, halfway through its journey, 4.7 trillion kilometers from Earth. A signal sent from mission control travels at light speed and takes 6 months to reach the probe. The probe's response takes another 6 months to return. Round-trip communication time, 1 full year. Any command sent from Earth reflects conditions that are at least a year old by the time the probe receives it. Any data transmitted by the probe describes events that occurred 6 months before Earth receives the information. For a mission lasting thousands of years at conventional speeds, this communication lag renders real-time control meaningless. The probe must operate with complete autonomy, making decisions based on its own sensors and programming, because the civilization that launched it cannot respond on timescales that matter. This autonomy requirement scales with distance and travel time in ways that challenge current engineering philosophy. Every robotic mission humanity has flown to date maintains some degree of ground control. Mars rovers receive daily command uploads. Deep space probes transmit telemetry and receive course corrections. Even Voyager 1, our most distant explorer, still communicates with Earth. Its radio signals take roughly 22 hours each way, a delay that is manageable for a spacecraft with no immediate navigational demands. But a probe crossing 1 light-year would face communication delays of months or years, operating in an environment where a single malfunction could be catastrophic and no help could possibly arrive in time. The light-year's time dimension also creates a strange philosophical consequence for interstellar travelers. A crew departing Earth on a 1 light-year journey would, for the duration of the transit, exist in a temporal no man's land. Their communications with Earth would be increasingly delayed. News from home would arrive months or years late. Replies to their messages would return long after the original context had faded. They would be physically present in the universe, alive and functioning, but informationally severed from the civilization that created them. The isolation is not just spatial, it is temporal. The travelers and their home world would occupy the same universe but increasingly different moments of it. This temporal isolation becomes even more extreme for longer journeys. A ship crossing 1 light-year at 1% of the speed of light would take 100 years. During that century, Earth would undergo transformations that the crew could not predict or participate in. The language, culture, technology, and political structures of their homeworld would evolve beyond recognition. If they could somehow return, they would arrive as strangers from a forgotten era. The light year is not just a measure of space, it is a measure of the separation between moments in cosmic history. There is one more aspect of the light year that demands attention before we confront the question of how to cross it. What this distance represents in the hierarchy of cosmic scales. Among the distances that astronomers routinely discuss, 1 light-year is small, vanishingly small. It is the entry-level unit of interstellar measurement, the equivalent of a single city block on a map of the globe. The nearest star system to our Sun Alpha Centauri lies approximately 4.37 light-years away. The brightest star in our night sky, Sirius, sits about 8.6 light-years from Earth. The center of our own Milky Way galaxy is roughly 26,000 light-years distant. The nearest major galaxy, Andromeda, floats 2.5 million light-years beyond that. The observable universe spans 93 billion light-years from edge to edge. In this hierarchy, 1 light-year occupies the very bottom rung. It is the minimum meaningful interstellar distance, the smallest gap between neighboring stellar systems. And yet, as we have seen, it already contains 9.46 trillion kilometers of vacuum, requires thousands of years to cross with any existing technology, and imposes communication delays that sever real-time contact between traveler and origin. If this is the smallest step, the first rung of the cosmic ladder, then the ladder itself ascends into distances that render even the light-year microscopic. This is why 1 light-year matters more as a concept than any specific destination. Popular discussions of interstellar travel tend to focus on targets Proxima Centauri, TRAPPIST-1, Kepler, 442b. These are fascinating worlds, but they distract from the deeper truth. The barrier is not the destination, the barrier is the distance itself. If you cannot cross 1 light-year in a reasonable time frame with a reasonable energy budget, then crossing 4 light-years is not merely a harder version of the same problem. It is 4 times impossible. 10 light-years is 10 times impossible. 100 light-years is 100 times impossible. The single light-year is the fundamental quantum of interstellar impossibility. Everything beyond it is multiplication. And here is where the standard narrative about interstellar travel usually offers a reassuring pivot. It says something like, yes, the distances are vast, but human ingenuity has always overcome obstacles. We went from horses to jets in a century. We went from Sputnik to the moon in 12 years. Surely we can solve this problem too, given enough time and enough funding. This optimism, while emotionally appealing, misunderstands the nature of the obstacle. The jump from horses to jets was a revolution in energy conversion. Chemical energy to mechanical thrust to aerodynamic lift. The jump from Sputnik to the moon was a revolution in rocket engineering. Larger engines, better guidance, more precise orbital mechanics. Both of these revolutions operated within the same basic framework of Newtonian physics. They improved the efficiency and scale of energy use, but they did not confront fundamental physical limits. 1 light year is different. It does not yield to incremental engineering improvements. Making a rocket engine 10% more efficient does not meaningfully change a 17,000-year travel time. Doubling the fuel capacity helps, but the rocket equation, the merciless logarithmic relationship between fuel mass and final velocity, ensures that doubling fuel does not double speed. It adds a fraction. The problem is not that we lack a sufficiently large rocket. The problem is that the velocity required to cross 1 light year in a human lifetime sits in a regime where the physics of energy, mass, and motion behave differently than they do in the comfortable Newtonian world of everyday engineering. Confronting 1 light year honestly means accepting that this distance is not simply very far. It is qualitatively different from anything humanity has crossed before. It exists in a regime where the constraints are not merely engineering challenges to be solved, but physical laws to be reckoned with. The speed of light is not a speed limit in the sense of a posted highway sign. It is woven into the geometry of space-time itself. Any technology that attempts to move mass across 1 light year must negotiate with this geometry, and the geometry does not negotiate back. It simply imposes its terms. 9.46 trillion kilometers, 63,000 astronomical units, 24.6 million Earth-Moon distances, less than 0.3% covered by Voyager 1 in 47 years. These are not just numbers. They are a declaration from the universe about the cost of crossing even the shortest interstellar distances. And the cost, as we are about to discover, is measured not in money, not in time alone, but in energy. Energy at scales that will force us to rethink what the word possible means. The question now becomes inescapable. Given this distance and everything it contains, the vacuum, the isolation, the communication delays, the sheer crushing scale, how long would it actually take to cross it? And the answer begins with the machines humanity already possesses, the chemical rockets and nuclear concepts that represent our best current technology. What you will find is that even our most powerful engines are barely capable of scratching the surface of 1 light year. And why that is true comes down to a single, elegant, devastating equation. Humanity's entire history of spaceflight can be summarized in a single, humbling sentence. We have learned to crawl magnificently within our own backyard. The rockets that carried astronauts to the moon, the probes that photographed every planet in our solar system, the rovers that drilled into Martian soil, these represent genuine triumphs of engineering, physics, and human determination. They are also, measured against the requirements of 1 light year, almost comically inadequate, not because they are poorly designed, not because the engineers who built them lacked vision, but because every propulsion system humanity has ever flown operates in a velocity regime so far below what interstellar distances demand that improving them is like upgrading from a rowboat to a speedboat and then pointing at the Pacific Ocean. To understand why, we need to start where rocketry starts, with the chemical engine. A chemical rocket works by burning propellant and directing the hot exhaust gases through a nozzle at high speed. The reaction between fuel and oxidizer releases energy stored in chemical bonds, and that energy accelerates the exhaust backward, pushing the rocket forward by Newton's third law. This is the fundamental mechanism behind every orbital launch vehicle in history, from the V-2 rockets of the 1940s to the Falcon 9 boosters landing on drone ships today. The physics is elegant, the engineering is mature, and the performance ceiling is absolute. The critical parameter for any rocket engine is its specific impulse, measured in seconds, which describes how efficiently the engine converts propellant into thrust. Specific impulse is directly related to exhaust velocity, the speed at which combustion products leave the nozzle. For the best chemical engines burning liquid hydrogen and liquid oxygen, the exhaust velocity tops out at approximately 4.4 to 4.5 kilometers per second. The RS-25 engine that powered the Space Shuttle main propulsion system achieved a vacuum-specific impulse of roughly 452 seconds, corresponding to an exhaust velocity of about 4 kilometers per second. This represents the practical ceiling for chemical propulsion. No clever nozzle geometry, no exotic propellant mixture, no advanced combustion technique can significantly exceed this value, because the energy available from chemical bonds has a fixed upper limit dictated by quantum mechanics and molecular physics. You cannot extract more energy from a chemical reaction than the reaction contains. 4.4 kilometers per second. Remember that number. It defines the exhaust velocity of the most efficient chemical engines humanity has ever built. Now compare it with the speed of light, 299,792 kilometers per second. The exhaust velocity of our best chemical rockets is roughly 1/68,000th of the speed of light. This ratio is the seed from which all the discouraging travel time numbers grow. The relationship between exhaust velocity and a rocket's achievable speed is governed by the Tsiolkovsky rocket equation, derived by Konstantin Tsiolkovsky in 1897. The equation is one of the most important results in astronautical engineering, and it is ruthless. It states that the change in velocity a rocket can achieve, called delta V, equals the exhaust velocity multiplied by the natural logarithm of the ratio between the rocket's initial mass, fully fueled, and its final mass after all propellant is expended. The logarithmic function is the critical detail. It means that increasing your fuel load does not increase your speed, proportionally. Doubling the fuel to payload ratio does not double your delta V. It adds only one more unit of exhaust velocity times the natural log of 2, which is approximately 0.693. To double your delta V, you must square the mass ratio. To triple it, you must cube it. Each additional increment of speed costs exponentially more propellant. This exponential scaling is often called the tyranny of the rocket equation, and the name is not dramatic enough. It is the single most important constraint in all of spaceflight, and it becomes absolutely devastating when applied to interstellar distances. To feel the tyranny viscerally, imagine you are designing a spacecraft. Your payload, the probe, the instruments, the structure, everything except fuel mass is 1,000 kilograms. You want to reach a modest speed, 10 kilometers per second. Your chemical engine has an exhaust velocity of 4.4 kilometers per second. The rocket equation tells you the mass ratio required is E raised to the power of 10 divided by 4.4, approximately e to the 2.27, which equals roughly 9.7. You need about 9.7 kilograms of fuel for every 1 kilogram of payload, so your fully fueled spacecraft mass is approximately 10,700 kilograms. Expensive, but manageable. This is roughly the regime of interplanetary probes. Now double your target speed to 20 kilometers per second. The mass ratio becomes e to the 4.55, approximately 94.6. You need 94.6 kilograms of propellant for every kilogram of payload. Your spacecraft now masses 95,600 kilograms, a dramatic increase for a mere doubling of speed. Push to 40 kilometers per second, and the mass ratio leaps to e to the 9.09, approximately 8,900. Your 1-ton payload now requires a fully fueled vehicle massing nearly 9,000 metric tons. Still physically possible, but the vehicle has become a flying fuel tank with a tiny payload riding at the tip. Now, attempt 100 kilometers per second, still only 0.03% of light speed. The mass ratio is e to the 22.7, approximately 7.2 billion. Your 1-ton payload needs 7.2 billion metric tons of fuel. That exceeds the mass of every object humanity has ever launched into space, combined, multiplied by a factor of roughly 1 million. And this is still 0.03% of light speed. To reach 1%, 3,000 kilometers per second, the mass ratio becomes e to the 682, a number so large it has no physical referent in the observable universe. You would need more fuel than there are atoms in every star in every galaxy across the observable cosmos. Chemical propulsion does not merely struggle with interstellar velocities. It is fundamentally, structurally, mathematically incapable of achieving them. The limitation is not technological, it is thermodynamic. The energy locked inside chemical bonds is simply too sparse, too dilute, too weak relative to the demands of traversing 9.46 trillion kilometers in any time frame shorter than geological epochs. So what speeds can chemical rockets actually achieve, and what do those speeds mean for crossing 1 light-year? The fastest departure velocity ever achieved by a spacecraft leaving the inner solar system under its own chemical propulsion before any gravitational assists is approximately 16.26 kilometers per second, achieved by the New Horizons mission at its initial Earth departure in 2006. After a gravitational slingshot past Jupiter, New Horizons reached a heliocentric velocity of roughly 23 kilometers per second. Voyager 1, whose 17 kilometer per second crawl we already examined, sits alongside these other probes in the same velocity neighborhood. The Pioneer 10 and 11 probes move at roughly 12 kilometers per second. These velocities represent the state-of-the-art for chemical plus gravity assist trajectories, the fastest speeds humanity has ever imparted to an object headed outward from the Sun. Take the highest of them. At 23 kilometers per second, New Horizons covers about 725 million kilometers per year. 1 light-year is 9.46 trillion kilometers. The crossing time is approximately 13,000 years. 13,000 years. If New Horizons had been launched toward a 0.1 light-year away on the day the last woolly mammoths walked the Earth, it would be arriving roughly now. The entire span of human civilization, the invention of writing, the rise of Egypt, Greece, Rome, the Middle Ages, the Renaissance, the Industrial Revolution, the space age fits comfortably within that transit window. Now consider a more optimistic chemical scenario. The Space Launch System, NASA's heavy lift vehicle, can place large payloads on fast interplanetary trajectories. A well-designed mission using the SLS with an optimized upper stage could potentially achieve departure velocities of 30 to 40 kilometers per second, with favorable gravitational assists. At 40 kilometers per second, an extremely generous estimate for any chemically launched spacecraft, 1 light-year requires approximately 7,500 years. Better than 13,000, certainly, but 7.5 millennia still exceeds the entire recorded history of most human civilizations. The conclusion is inescapable. Chemical propulsion, the only technology we have actually used for interplanetary travel, is structurally incapable of crossing interstellar distances in any time frame meaningful to human beings. It would take hundreds of generations, thousands of years, epochs of history. The technology works brilliantly for reaching the Moon in 3 days, Mars in 7 months, Jupiter in a few years, and Pluto in a decade. But 1 light-year exposes chemical rocketry as a local transportation system, magnificently suited to the solar neighborhood and hopelessly outmatched by the interstellar void. So engineers and physicists looked beyond chemistry. The obvious next step was nuclear energy. Nuclear thermal propulsion replaces the chemical combustion chamber with a nuclear fission reactor. Instead of burning hydrogen and oxygen together, the engine passes a working fluid, typically pure hydrogen, through the core of a reactor, heating it to extreme temperatures, and then expelling it through a nozzle. Because the energy source is nuclear fission rather than chemical combustion, the energy per unit mass of fuel is roughly 1 million times higher. This does not translate into a million-fold improvement in exhaust velocity, because the exhaust velocity depends on the temperature and molecular weight of the expelled gas, not directly on the energy content of the fuel. But the improvement is substantial. Nuclear thermal engines achieve exhaust velocities of approximately 8 to 9 kilometers per second, roughly double that of the best chemical engines. This is not theoretical. The United States built and tested nuclear thermal rocket engines during the 1960s under Project Nerva, which stood for Nuclear Engine for Rocket Vehicle Application. The program's engines worked. They produced thrust. They demonstrated specific impulses of approximately 850 seconds, nearly double the Space Shuttle's main engines. The technology was proven, shelved for political and budgetary reasons, and has recently attracted renewed interest for crewed Mars missions. But doubling the exhaust velocity, while significant for solar system missions, barely dents the interstellar problem. Plug the improved numbers into the rocket equation. To reach 1% of light speed using nuclear thermal propulsion with an exhaust velocity of 9 kilometers per second, the required mass ratio is e to the power of 3000 divided by 9, approximately e to the 333 power. Still a number vastly larger than the mass of the observable universe. The logarithmic tyranny of the rocket equation means that doubling exhaust velocity merely halves the exponent, which does almost nothing when the exponent starts in the hundreds. Realistically, a nuclear thermal spacecraft could achieve delta-V values of perhaps 20 to 40 kilometers per second, depending on how aggressively the reactor is operated and how much propellant is carried. At the high end, 40 kilometers per second, the 1 light-year crossing time is the same 7,500 years we calculated for the most optimistic chemical scenario. The advantage of nuclear thermal over chemical is not speed, it is efficiency. A nuclear thermal vehicle achieves the same velocity with less propellant, which matters enormously for solar system missions where every kilogram of fuel costs money to launch. But for interstellar travel, efficiency gains within the same velocity regime change nothing fundamental. 7,500 years is just as impossible as 13,000 years when your benchmark is a human lifetime. Nuclear electric propulsion offers a different trade-off. Instead of heating propellant directly, a nuclear reactor generates electricity, which powers an ion drive or plasma thruster. These engines achieve much higher exhaust velocities, 30 to 50 kilometers per second for current ion drives, and potentially 200 or more kilometers per second for advanced magnetoplasma-dynamic thrusters. The trade-off is thrust. Ion engines produce tiny amounts of force millinewtons, rather than the meganewtons of a chemical rocket. They cannot launch from a planet's surface. They cannot perform rapid maneuvers. What they can do is accelerate continuously for months or years, gradually building up enormous velocities through patient, persistent thrust. A spacecraft equipped with an advanced nuclear electric propulsion system might, over several years of continuous thrusting, reach velocities of 100 to 200 kilometers per second. At 200 kilometers per second, 1 light-year requires approximately 1,500 years. A dramatic improvement over chemical rockets, but still a time frame that spans more than the entire period since the fall of the Roman Empire. No human crew can survive a 1,500-year journey. No electronic system can operate reliably for that duration. No political or cultural institution can maintain a mission for 60 generations. This is where nuclear pulse propulsion enters the conversation, and the tone of the entire discussion shifts. Nuclear pulse propulsion is not a refinement of existing technology. It is a fundamentally different philosophy of force, one that was studied in remarkable detail during the late 1950s and early 1960s under Project Orion at General Atomics in San Diego. The concept is startling in its directness. Detonate nuclear bombs behind a spacecraft, ride the blast waves, Each detonation propels a pulse of superheated plasma into a massive pusher plate mounted at the rear of the vehicle. The plate absorbs the impact, transfers the momentum through a set of enormous shock absorbers, and the ship lurches forward. Then you detonate another bomb, and another, and another. Hundreds of them. Thousands. The vehicle surfs a chain of nuclear explosions across the solar system and beyond. It sounds reckless. It is reckless. But the physics is extraordinarily favourable. Nuclear explosions release energy at densities that dwarf anything achievable by controlled combustion or steady-state reactors. The effective exhaust velocity of a nuclear pulse drive depends on the bomb yield and the efficiency of momentum transfer, but credible estimates range from roughly 200 to 400 kilometers per second for fission devices, and potentially several thousand kilometers per second for optimized thermonuclear fusion devices. These numbers change the interstellar calculation dramatically. The original Project Orion studies envisioned vehicles of extraordinary scale. The largest proposed design, sometimes called the Super Orion, massed approximately 8 million metric tons and was intended for interplanetary missions with enormous payload capacity. It could carry entire cities' worth of equipment and passengers to Mars or the outer planets. Smaller designs, in the range of tens of thousands to hundreds of thousands of metric tons, were studied for faster interstellar precursor missions. The physicist Freeman Dyson, who contributed to the Orion studies and later became one of its most eloquent advocates, spent years analysing the interstellar potential of nuclear pulse vehicles. Dyson calculated that a dedicated interstellar Orion variant using optimized fusion pulse units could theoretically reach 3 to 5% of the speed of light. The team working on Orion at General Atomics was not a collection of dreamers. It included Ted Taylor, one of the most gifted nuclear weapon designers in American history, a man who had designed both the smallest and the most efficient fission weapons in the United States arsenal. It included Dyson, who had become one of the 20th century's most influential theoretical physicists. They conducted actual experiments. Small-scale tests using conventional chemical explosives demonstrated that the pusher plate concept worked. A steel plate could absorb repeated explosive impacts and transfer momentum to a vehicle without being destroyed. The physics scaled. The engineering was aggressive but grounded in real metallurgy and real thermodynamics. For a brief period in the early 1960s, a genuine interstellar mission seemed like something achievable within a few generations of sustained technological development. At 3% of light speed, approximately 9,000 kilometers per second, 1 light year requires about 33 years. At 5%, 15,000 kilometers per second, the transit drops to roughly 20 years. Stop and absorb what just happened. We began this section with chemical rockets requiring 13,000 years. We moved through nuclear thermal at 7,500. Nuclear electric brought it down to 1,500. And now, nuclear pulse propulsion has slashed the number to 20 or 30 years. For the first time in this entire analysis, we have entered the territory of a single human lifetime. An astronaut departing Earth at age 30 aboard a 5% light-speed Orion vessel would arrive at the 1 light-year mark around age 50. Still alive, still functional, still young enough to operate instruments, collect data, and transmit findings back to Earth. The number is no longer abstract. It is biographical. These numbers electrified the physicists working on Orion. They sketched mission profiles. They debated crew sizes. They estimated the mass of nuclear pulse units required and the thickness of the pusher plate and the optimal detonation interval. For a few years, the interstellar void looked conquerable not easily, not cheaply, but conquerable within the framework of known physics and achievable engineering. But the obstacles were formidable, and they killed the project before it could mature. The first and most immediate obstacle was political. The Partial Test Ban Treaty of 1963 prohibited nuclear weapon detonations in outer space, in the atmosphere, and underwater. Orion required detonating hundreds or thousands of nuclear devices in space. The treaty made the concept illegal under international law. Even before the treaty, concerns about radioactive fallout from launch. The vehicle would need to detonate its first bombs while still within or very near Earth's atmosphere to build initial velocity generated intense opposition from scientists, politicians, and the public. The environmental cost of an Orion launch would be measured in nuclear contamination spread across the upper atmosphere, a price that no government was willing to pay in an era already haunted by the spectre of fallout from atmospheric weapons testing. The second obstacle was engineering scale. An interstellar Orion vehicle would need to carry thousands of nuclear pulse units, each one a precisely designed nuclear device with specific yield characteristics, detonation timing, and directional shaping. Each one stored safely for decades of transit. Each one detonated in exact sequence at precise intervals. The pusher plate, a massive disc of high-strength steel or advanced alloy, would need to withstand repeated nuclear blasts at close-range temperatures of millions of degrees, pressures exceeding any terrestrial explosion without cracking, warping, eroding, or losing structural integrity over thousands of cycles. The shock absorption system would need to convert violent, irregular impacts into smooth, sustained acceleration tolerable by a crew and a vehicle structure. The engineering required is within the realm of known materials science, but the scale is entirely unprecedented. No structure remotely this large, this resilient, or this precisely managed has ever been built or even tested at full scale. The third obstacle was fuel supply. Even for a fusion-optimized Orion, the mass of nuclear pulse units required for an interstellar mission would be staggering. The original studies estimated that an interstellar Orion variant might need a total vehicle mass of several 100,000 metric tons, the vast majority of which would be pulse units. Manufacturing, storing, arming, and safely handling that quantity of nuclear material across decades of assembly and flight represents an industrial and logistical challenge without precedent in human history. And there is a subtler problem that applies to all nuclear pulse concepts. Even at 5% of light speed, the vehicle takes 20 years to cross 1 light year. During those 20 years, the crew lives aboard a ship that was accelerated by nuclear detonations. The residual radiation environment is intense. Shielding the crew from neutron flux, gamma radiation, and secondary particle showers produced by each detonation requires massive radiation barriers, which add to the vehicle's total mass, which requires more pulse units to accelerate, which adds more mass, which requires still more pulse units. The rocket equation, though less punishing at the energy densities of nuclear explosions, still applies. The spiral of mass begetting more mass continues. There is a further category of nuclear propulsion that deserves attention: the fission fragment rocket. Unlike conventional nuclear thermal engines, which heat a working fluid and expel it, fission fragment rockets would directly channel the high-energy fragments produced by nuclear fission particles, moving at 3 to 5% of the speed of light out of the engine as exhaust. The theoretical exhaust velocity is extraordinary, potentially matching or exceeding the velocities achieved by nuclear pulse drives, but in a controlled, continuous thrust mode rather than a pulse detonation mode. The concept remains deeply theoretical. Containing and directing fission fragments requires magnetic nozzle technology that does not yet exist at the required scale or efficiency. The reactor design would need to sustain fission reactions while allowing most of the reaction products to escape rather than being captured within the fuel structure. Material science, plasma physics, and magnetic confinement all pose unsolved challenges, but if fission fragment rockets could be built, they would offer exhaust velocities in the range of 3,000 to 5,000 kilometers per second, high enough to push a spacecraft to several percent of light speed without the political and environmental liabilities of detonating nuclear weapons in open space. At 5% of light speed, the travel time across 1 light year holds steady at 20 years, a meaningful improvement over chemical and nuclear thermal systems, but still a long journey, and 20 years assumes you do not need to slow down at the other end. Deceleration requires carrying additional fuel or finding another way to shed velocity, neither of which is trivial at these speeds. What all of these nuclear concepts share, from the mundane thermal engines to the dramatic pulse drives, is a common underlying architecture. The vehicle carries its own energy source and expels mass to generate thrust. Whether that mass is heated hydrogen, fission bomb plasma, or high-speed fission fragments, the principle is the same. Momentum is transferred by throwing stuff backward, and the rocket equation governs this process with mathematical impartiality, ensuring that the relationship between fuel mass and final velocity remains logarithmic, punishing, and ultimately limiting. The rocket equation does not care about the energy source. It cares about the exhaust velocity and the mass ratio. Improve the exhaust velocity by a factor of 10, and the required mass ratio drops, but it drops from absurdly large to merely enormous. Improve it by a factor of 100, and the mass ratio becomes manageable, but the engineering required to achieve exhaust velocities 100 times better than chemical rockets pushes into territory that no laboratory on Earth has demonstrated. This is the fundamental lesson of this section. Every propulsion concept that carries its own fuel is bounded by the rocket equation. Chemical rockets hit the wall at a few tens of kilometers per second. Nuclear thermal engines push to perhaps 40 or 50. Nuclear electric systems might reach 1 to 200. Nuclear pulse drives can potentially achieve several thousand. Fission fragment rockets could theoretically match that range. Each step buys a significant reduction in travel time, from millennia to centuries to decades. But each step also demands exponentially greater engineering ambition, industrial capacity, and tolerance for nuclear risk. And none of them, not one, escape the rocket equation's fundamental constraint. As long as the spacecraft must carry its own propellant, the relationship between desired velocity and required fuel mass grows exponentially. There is always a ceiling. For nuclear pulse, that ceiling sits around 5 to perhaps 8% of light speed under the most optimistic assumptions. For fission fragment, maybe 10%. Beyond that, the mass ratios become impractical even for nuclear energy densities. 10% of light speed yields a 1 light-year transit of roughly 10 years. Not bad. Not fast enough to feel routine, but within the span of a human career. The problem is that reaching even 10% demands vehicle masses, fuel supplies, and engineering capabilities that exceed anything currently on the drawing board by orders of magnitude. So the question sharpens. If carrying your own fuel limits you to single-digit percentages of light speed, what happens when you abandon the fuel entirely? What if the energy stays home and only the spacecraft travels? What if you push with light itself, or with magnetic fields, or with the fabric of space? These ideas sound like science fiction, and some of them are. But a few have been studied with enough rigor to produce real numbers, real engineering assessments, and real confrontations with the physics of interstellar travel. The most promising of these concepts can, in theory, push tiny spacecraft to 20% of the speed of light or more, and at 20% of light speed, 1 light-year passes in just 5 years. But as we are about to discover, even the most radical propulsion concepts carry penalties that grow savage as the velocities climb, and the universe, it turns out, has a few more walls waiting beyond the rocket equation. Every propulsion concept examined so far shares one architectural feature. The spacecraft drags its energy source along for the ride. Whether that energy is locked inside chemical bonds, fission fragments, or thermonuclear pulse units, the vehicle must carry it, accelerate it, and expend it gradually as the mission unfolds. The rocket equation governs this architecture with absolute authority, imposing exponential penalties on every kilogram of fuel added to the stack. And as we have seen, those penalties set a practical ceiling somewhere around 5 to 10% of the speed of light, even for the most energetic nuclear concepts ever seriously proposed. But there is another way. What if the spacecraft carried no fuel at all? What if the energy source stayed home fixed to the ground, mounted in orbit, or powered by the sun, and the vehicle travelled empty, pushed from behind by a beam of concentrated power? This idea is not new. It dates back to at least the 1960s, when physicist Robert Forward first proposed using laser beams to accelerate interstellar light sails. But it took half a century for the concept to evolve from a physicist's daydream into a funded engineering study with named hardware, identified materials, and a specific target velocity. That study is called Breakthrough Starshot, and it represents the most serious attempt in human history to design a system capable of reaching a significant fraction of light speed. The core physics is elegant. Photons carry momentum. When a photon reflects off a mirror, it transfers twice its momentum to the mirror's surface, once on arrival, once on departure. A single photon's momentum is absurdly small, but gather enough photons into a coherent beam and aim them at a lightweight reflective surface, and the accumulated momentum transfer becomes substantial. The critical advantage is that the energy source, the laser, stays behind. It never needs to be accelerated. Its mass is irrelevant to the spacecraft's velocity. The rocket equation, which demands that every gram of onboard fuel be paid for with exponentially more fuel, simply does not apply. The vehicle carries nothing but payload and sail. The beam provides everything. Breakthrough Starshot, announced in April 2016, with initial funding of $100 million from investor Yuri Milner and public support from the late Stephen Hawking, proposed a specific implementation of this concept. The plan envisions a phased array of ground-based or space-based lasers, producing a combined beam power of approximately 100 gigawatts. That is roughly the total installed electrical generation capacity of a country like France or the United Kingdom, channeled into a single coherent beam aimed at a target smaller than a dinner table. The beam would illuminate a light sail approximately 4 meters in diameter, constructed from an advanced material that is simultaneously highly reflective, extraordinarily lightweight, and capable of surviving intense thermal loads without melting or deforming. Attached to the sail would be a payload chip, a gram-scale integrated circuit containing a camera, a photon communication laser, a basic processor, and a power source. The total mass of the sail chip assembly, roughly 1 to 10 grams, depending on the design iteration. Under 100 gigawatts of focused laser illumination, this gossamer vehicle would accelerate ferociously. The acceleration would exceed 10,000 times Earth's gravity for several minutes, pushing the sail-chip combination to approximately 20% of the speed of light, about 60,000 kilometers per second, before the beam loses focus and the spacecraft begins coasting. At 20% of light speed, 1 light year passes in 5 years. The system transitions from the millennia-scale crawl of chemical rockets, past the decade-scale transit of nuclear pulse drives, into a regime where interstellar distances shrink to something resembling a long but finite research mission. 5 years. The number is seductive. It fits within a grant cycle, a doctoral program, a presidential administration. It suggests that interstellar travel, at least for tiny robotic probes, might be achievable within the lifetime of people alive today, and the physics supporting it is sound. Radiation pressure is a measured phenomenon. Photon momentum transfer has been demonstrated in laboratories. There is no exotic physics required, no undiscovered particles, no speculative warp fields. Everything about the Starshot concept relies on known science applied at unprecedented scale. But unprecedented scale is where the seduction ends and the engineering nightmares begin. The laser array is the first and most formidable challenge. 100 gigawatts of coherent, phase-locked laser power does not exist anywhere on Earth. The most powerful continuous wave lasers currently in operation produce on the order of tens to hundreds of kilowatts, roughly 6 orders of magnitude below the Starshot requirement. Bridging that gap demands a phased array of potentially millions of individual laser emitters, each one precisely synchronized with its neighbors so that their beams combine constructively at a focal point, light minutes away. The phase coherence requirements are measured in fractions of the laser's wavelength, nanometers of precision, maintained across an array spanning kilometers of physical extent. Atmospheric turbulence, thermal distortion, mechanical vibration, and timing jitter all conspire to destroy coherence. Adaptive optics systems would need to correct for these distortions in real time, adjusting millions of emitter phases thousands of times per second. Consider what this means practically. Each laser emitter in the array must know its own position relative to every other emitter, to within a fraction of the operating wavelength, roughly 1 micrometer for a near-infrared laser. This precision must be maintained not across a laboratory bench, but across a structure spanning several kilometers, exposed to wind loads, seismic vibrations, thermal expansion, and the constant flexing of its own support structure. The control system managing phase coherence across millions of emitters must operate at microsecond timescales, processing sensor data and adjusting emitter phases faster than the atmosphere can distort the beam. Existing phased array technology in radar systems achieves comparable coherence, but at radio wavelengths thousands of times longer than optical light, which makes the engineering tolerances thousands of times more forgiving. Scaling those techniques to optical wavelengths across kilometer baselines represents a development effort that the Starshot team itself estimates will require decades. The sail material poses equally daunting requirements. At 100 gigawatts of illumination concentrated on a 4-meter disk, the energy flux at the sail surface is approximately 8 gigawatts per square meter. For comparison, the solar flux at Earth's orbital distance is about 1,360 watts per square meter. The Starshot sail would endure an energy flux roughly 6 million times the intensity of sunlight. Any material that absorbs even a tiny fraction of this energy will heat catastrophically. The sail must reflect upward of 99.99% of incident light at the laser's wavelength. No material currently manufactured achieves this reflectivity at the required thinness. The sail must mass only grams, implying a thickness of perhaps 100 to 1,000 nanometers. To appreciate how thin that is, consider that a human red blood cell is roughly 2,000 nanometers thick. The Starshot sail would be thinner than half a blood cell, stretched across an area of more than 12 square meters, subjected to accelerations exceeding 10,000 times Earth's gravity. If the sail absorbs even 0.01% more light than its design tolerance allows, the absorbed energy heats the material by thousands of degrees within milliseconds. The sail does not merely deform, it vaporizes. The margin between mission success and complete destruction is measured in fractions of a percent of reflectivity, a tolerance that current materials science has never been asked to achieve at this scale. Candidate materials include engineered metamaterials, photonic crystal structures, and advanced dielectric multi-layer coatings, all of which exist in laboratory demonstrations at centimeter scales, but have never been produced at the meter scale areas required. Manufacturing a 4-meter diameter sail with uniform reflectivity exceeding 99.99%, uniform thickness below 1 micrometer, and sufficient structural integrity to survive 10,000 G acceleration is a materials engineering challenge without precedent. It may be solvable, but solving it requires breakthroughs in thin film deposition, quality control at atomic scales, and structural mechanics of nanoscale membranes that the field has not yet demonstrated. Beam divergence imposes a fundamental range limit on the acceleration phase. No laser beam is perfectly collimated. Diffraction causes any beam to spread as it propagates, and the rate of spreading depends on the beam's wavelength and the diameter of the emitting aperture. For a 1 micrometer wavelength laser emitted from a kilometer scale array, the beam remains reasonably focused for a distance of roughly 50 million to 100 million kilometers, a few tenths of an astronomical unit. Beyond that distance, the beam spot grows larger than the sail, and the energy delivered per unit area drops below useful levels. This means the entire acceleration phase from rest to 20% of light speed must be completed within the first few minutes of flight, while the spacecraft is still close enough for the beam to remain focused. After that, the sail chip is on its own, coasting through the interstellar void at 60,000 kilometers per second with no ability to adjust course, no way to decelerate, and no possibility of a second acceleration phase. If the trajectory is slightly off by fractions of a degree, the probe will miss its target by billions of kilometers. Precision aiming must be achieved entirely during the brief acceleration window, with corrections measured in nanoseconds of beam timing adjustment across the phased array. And then there is the question of what happens when the probe arrives. At 20% of light speed, a flyby of any object at the 1 light-year mark lasts minutes at most. The probe screams past at 60,000 kilometers per second, snapping images and collecting data during an encounter window, so brief that the target transitions from distant point to visible object to receding speck in less time than a commercial break. Whatever science the mission collects must be gathered in that window and then transmitted back to Earth using a tiny onboard laser, a signal that will take 1 year to arrive and will be so faint by the time it reaches the inner solar system that detecting it will require receiver arrays rivaling the transmitter in scale and sensitivity. There is no stopping. A light sail pushed from behind has no mechanism for deceleration at the destination. The beam is 100 million kilometers behind. There is nothing ahead to push against. The interstellar medium is too sparse to provide meaningful drag. Unless a second laser array has been pre-positioned at the destination, which would require a prior mission, which raises the question of how you decelerate that mission. The probe flies through and keeps going forever. Laser propulsion buys speed by sacrificing versatility. The vehicle is a bullet, not an explorer. Some theorists have proposed partial solutions. Robert Forward suggested a 2-stage light sail, where a large outer ring detaches at the halfway point and reflects the beam back onto a smaller inner sail, decelerating it. The physics works in principle, but the engineering tolerances are punishing. The detached ring must maintain its shape and reflectivity. After separation, the reflected beam must hit the smaller sail accurately across millions of kilometers, and the deceleration forces must not destroy the payload. No working prototype of this concept has ever been built, and the precision required for beam redirection across interstellar distances remains far beyond current optical engineering. Starshot also faces the hostility of the interstellar medium itself. At 20% of light speed, even the sparse hydrogen atoms populating the void become a hazard. Each hydrogen atom encountered by the spacecraft's forward surface carries a kinetic energy proportional to the square of the velocity. At 60,000 kilometers per second, individual atom impacts carry energies of roughly 19 megaelectron volts, already in the range of particles produced by small research cyclotrons. Over 1 light-year, the cumulative bombardment deposits significant energy into the sail, potentially eroding its surface, degrading its reflectivity, and generating secondary radiation that damages the delicate electronics of the payload chip. Interstellar dust grains compound the problem enormously. A single grain massing 1 microgram, far too small to see with the naked eye, striking the sail at 20% of light speed, would release kinetic energy equivalent to a small explosive charge. A grain massing 1/10 of a milligram impacts, with the energy of roughly 43 kilograms of TNT equivalent to a heavy artillery shell. Over a 1 light-year traverse, statistical models of the interstellar dust distribution suggest the spacecraft would encounter thousands of microgram-class grains and potentially dozens of larger ones. Each impact is a dice roll against mission survival, and the odds worsen with every additional light-year of travel. The Starshot concept thus occupies a strange middle ground. Its physics is valid, its target velocity is genuinely useful for interstellar scales, but its achievable payload grams is too small for anything except a bare minimum flyby reconnaissance. And the engineering required to build the laser array, fabricate the sail, aim the beam, survive the interstellar medium, and collect useful data during a seconds-long encounter pushes every relevant technology to its theoretical limit simultaneously. Starshot is not impossible. It is merely extraordinarily difficult, expensive, and limited in what it can accomplish. For missions requiring larger payloads, longer observation windows, or most critically the ability to decelerate at the destination, a different approach is needed. And that brings us to fusion propulsion. Fusion, the process that powers the sun, releases energy by combining light atomic nuclei into heavier ones. When two deuterium nuclei fuse, or when deuterium fuses with helium-3 or tritium, the reaction products carry enormous kinetic energy that can, in principle, be directed out of a magnetic nozzle to generate thrust. The energy yield per kilogram of fusion fuel exceeds that of fission by a factor of roughly 4 to 10, depending on the reaction. And unlike chemical or fission propulsion, where much of the reaction energy is lost to non-useful radiation, certain fusion reactions produce charged particles that can be magnetically steered, offering the possibility of extremely high exhaust velocities. The most detailed fusion starship design ever produced is Project Daedalus, a study conducted by members of the British Interplanetary Society between 1973 and 1978. Daedalus was designed to reach Barnard's star, approximately 6 light-years from the Sun, within a 50-year flight time. The vehicle would use inertial confinement fusion, igniting tiny pellets of deuterium and helium-3, using high-energy electron beams fired from multiple directions simultaneously. Each pellet, roughly the size of a marble, would be compressed and heated to temperatures exceeding 100 million degrees in a fraction of a microsecond, triggering a fusion microexplosion. The resulting plasma, channeled and directed by powerful magnetic fields, would be expelled through a magnetic nozzle at velocities of roughly 10,000 kilometers per second. The ship would accelerate for approximately 3.8 years, reaching a cruise velocity of roughly 12% of the speed of light, about 36,000 kilometers per second. At 12% of light speed, 1 light-year requires approximately 8.3 years of coasting. Including the acceleration phase, the total 1 light-year transit comes to roughly 9 to 10 years. This is within a single human career. An astronaut could depart, arrive, conduct observations, and still have decades of productive life remaining. The number alone represents a staggering achievement of theoretical engineering, but the vehicle that achieves this performance is monstrous. Daedalus's total launch mass was estimated at 54,000 metric tons, of which roughly 50,000 tons constituted propellant deuterium and helium-3 fuel pellets. The payload was 450 metric tons, less than 1% of the total vehicle mass. Everything else was fuel and engine. The vehicle was, in essence, a flying fuel depot with a thin veneer of instruments bolted to the front. The helium-3 requirement alone presents a supply chain problem of interplanetary proportions. Helium-3 is vanishingly rare on Earth. Total terrestrial reserves amount to perhaps a few tens of kilograms, trapped in geological formations or accumulated from decades of tritium decay in nuclear weapon stockpiles. Daedalus required roughly 30,000 metric tons of helium-3. The only known source with sufficient abundance is the atmosphere of Jupiter, where helium-3 exists as a trace component of the planet's vast hydrogen-helium envelope. The Daedalus study assumed that robotic aerostats, balloon-borne factories drifting through the Jovian cloud layers at altitudes where atmospheric pressure and temperature permit stable operation would scoop gas, extract the helium-3 through cryogenic separation processes, and launch refined fuel pellets to orbital collection depots for transfer to the waiting starship. Pause and consider what this entails. Before the interstellar mission even begins, humanity would need to establish a permanent industrial presence in the atmosphere of Jupiter. Automated factories would need to operate continuously in an environment of crushing pressures, corrosive chemistry, extreme wind shear, and intense radiation from Jupiter's magnetosphere. The extracted helium-3 would need to be launched from Jupiter's enormous gravity, 63 times the surface gravity of Earth, to orbital staging points, then transferred across the inner solar system to the construction site of the starship. This supply chain alone, the Jovian mining infrastructure, the orbital fuel depots, the interplanetary tanker fleet, would constitute the largest engineering project in human history, dwarfing the Apollo program by orders of magnitude in cost, complexity, and duration. and all of it would be merely the fuel supply for the actual mission. Project Icarus, a 21st century successor study launched in 2009 and completed over several years of collaborative work, revisited the Daedalus concept with updated physics, engineering, and materials science. Icarus explored multiple fusion fuel cycles, including deuterium-deuterium reactions that avoid the helium-3 supply problem entirely. Deuterium is abundant in seawater. Approximately 1 in every 6,500 hydrogen atoms in Earth's oceans is deuterium. Extracting it is straightforward and inexpensive. The global ocean contains enough deuterium to fuel fusion reactors for billions of years, but deuterium-deuterium fusion is harder to ignite than deuterium-helium-3, requires higher confinement temperatures, produces significantly more neutron radiation that damages engine components and irradiates the crew, and yields lower exhaust velocities than the cleaner helium-3 reaction. Icarus designs, using deuterium-deuterium fuel, achieved estimated cruise velocities of 5 to 10% of light speed, somewhat lower than Daedalus, with correspondingly longer transit times of 10 to 20 years per light year. Both Daedalus and Icarus share a fundamental limitation. They are uncrewed flyby probes. Neither design includes the ability to decelerate at the destination. Like Starshot, they are sprinters built without brakes designed for velocity, not arrival. A Daedalus-class vehicle would cross 1 light-year in under a decade, scream past anything in its path at 12% of light speed, and continue into the void beyond. Adding deceleration capability roughly doubles the fuel requirement, because slowing down from 12% of light speed demands the same energy as speeding up. The total vehicle mass would approach or exceed 100,000 metric tons, and the fuel supply challenge already requiring the industrialization of Jupiter's atmosphere would worsen proportionally. For a crewed mission, the numbers become far more severe. A minimal crewed vessel carrying even a small team, life support for a decade or more, radiation shielding against cosmic rays and fusion byproducts, enough habitat space to prevent psychological collapse, medical facilities, redundant systems for every critical function, and the structural mass to hold it all together would mass at minimum hundreds of thousands of kilograms. Scaling Daedalus's propellant-to-payload ratio to a crewed vehicle yields total launch masses in the range of millions to tens of millions of metric tons. Manufacturing, assembling, and fueling such a vehicle in orbit would require a space-based industrial infrastructure that does not exist and would itself take decades or centuries to develop. And all of this assumes that fusion propulsion works as theorized. As of the present year, no fusion reactor on Earth has achieved sustained net energy gain, the condition where the reactor produces more energy from fusion than is consumed to initiate and maintain the reaction. This milestone, pursued for over 70 years at a cumulative cost exceeding hundreds of billions of dollars, remains elusive. Recent experiments at the National Ignition Facility have demonstrated fusion ignition, a brief moment where the fusion fuel produced more energy than the laser delivered to it, but sustained, repeatable, net positive fusion remains a laboratory goal, not an operational reality. Building a fusion reactor that works reliably inside a spacecraft, sustaining reactions continuously for years of powered flight, and converting the reaction products into directed thrust through magnetic nozzles that do not erode or fail. This chain of engineering achievement stretches far beyond the current state of the art. There are even more exotic concepts worth examining, though each comes burdened with progressively heavier caveats. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, envisioned a spacecraft that harvests its own fuel from the interstellar medium while in flight. An enormous magnetic funnel, potentially hundreds of kilometers in diameter, would scoop interstellar hydrogen from the vehicle's path, compress it, and feed it into an onboard fusion reactor. The appeal is overwhelming. No need to carry fuel at all. The interstellar medium becomes an infinite gas tank. As the ship accelerates, it encounters more hydrogen per second, which feeds more fusion reactions, which provides more thrust. In theory, the ramjet could accelerate continuously for years, eventually approaching the speed of light. Subsequent analysis deflated this vision considerably. The interstellar medium contains roughly 1 hydrogen atom per cubic centimeter, at the velocities needed to scoop meaningful quantities of fuel. The drag created by the magnetic funnel, the electromagnetic resistance encountered while sweeping charged particles into the collection field, likely exceeds the thrust produced by fusing the collected hydrogen. The ramjet may actually function as a brake rather than an engine. Several studies in the 1970s and 80s concluded that a pure Bussard ramjet cannot accelerate in the real interstellar medium. The fuel is simply too sparse and the collection penalty too high. Modified versions that carry initial fuel supplies and use the ramjet as a supplemental source show marginal improvements, but none achieve the continuous acceleration that made the original concept so attractive. Antimatter propulsion sits at the opposite extreme of the energy spectrum. When a particle of matter meets its corresponding antiparticle, they annihilate completely, converting 100% of their combined rest mass into energy. This is the highest energy-to-mass conversion ratio permitted by physics. 1 gram of antimatter annihilating with 1 gram of ordinary matter releases approximately 1.8 times 10 to the 14th joules, the energy equivalent of roughly 43 kilotons of TNT. A few tens of kilograms of antimatter, paired with an equal mass of ordinary matter, could theoretically accelerate a spacecraft to significant fractions of light speed with a mass ratio that the rocket equation would find perfectly acceptable. The obstacles are not theoretical, they are practical, and they are currently insurmountable. The total quantity of antimatter produced by every particle accelerator on Earth since the discovery of the positron in 1932 amounts to roughly 20 nanograms, 20 billionths of a gram. Producing antimatter in useful quantities requires particle accelerators of extraordinary power, and the production process consumes far more energy than the antimatter stores. Antimatter is not an energy source. It is an energy storage medium with a manufacturing efficiency of roughly 1/10 billionth. Producing 1 gram of antimatter using current technology would cost approximately $25 trillion and would require the total electrical output of the United States running for roughly a year. Storing antimatter poses its own existential challenge. Antimatter cannot touch ordinary matter. Any contact results in immediate annihilation. Charged antiparticles can be confined in magnetic traps called penning traps, where electromagnetic fields suspend the particles in vacuum without allowing wall contact. Current penning traps store antiprotons for months at a time, but the quantities stored are measured in millions of individual particles, far less than a nanogram. Scaling from millions of antiprotons to the kilograms required for a Starship engine represents an increase of roughly 25 orders of magnitude. No credible pathway from current storage capabilities to Starship-scale antimatter containment has been identified. And even if antimatter could be produced and stored in sufficient quantities, the annihilation products pose severe challenges for propulsion. Proton-antiproton annihilation produces a shower of pions, which decay into muons, which decay into electrons, positrons, and neutrinos. A significant fraction of the annihilation energy is carried away by neutrinos, which interact with essentially nothing and cannot be directed for thrust. The remaining energy is distributed among charged particles moving in various directions. Capturing and directing these particles through a magnetic nozzle to produce useful thrust requires engineering that no existing design has solved at high efficiency. Each of these advanced concepts, laser sails, fusion drives, ramjets, antimatter engines, follows a pattern that by now should feel familiar. Genuine physical insight identifies a mechanism that could, in principle, push a spacecraft to interstellar velocities. Detailed analysis reveals engineering obstacles that range from merely colossal to fundamentally unsolved. Estimated performance falls somewhere between impressive and revolutionary, but always comes with caveats that limit practical application to specific payload ranges, mission profiles, or technology readiness levels that do not yet exist. Laser sails can reach 20% of light speed, but carry only grams of payload and cannot stop. Fusion drives can push thousands of tons to 5 or 12% of light speed, but require fuel quantities that demand the industrialization of other planets, and fusion technology that does not yet work at any scale. Ramjets promise unlimited acceleration, but probably cannot overcome their own collection drag in the real interstellar medium. Antimatter offers the highest energy density in physics, but exists in quantities measured in billionths of a gram, costs more than the global economy to produce, and annihilates its container if containment fails for a microsecond. What emerges from this survey is not despair but clarity. Crossing 1 light year in a time frame relevant to human life, 5 years, 10 years, 20 years, requires velocities in the range of 10 to 20% of the speed of light. Achieving those velocities is not forbidden by physics. Multiple propulsion concepts, grounded in real science and studied by serious engineers, can theoretically reach this performance envelope. The barrier is not knowledge, it is capability. The gap between understanding how to reach 10% of light speed and actually building a vehicle that does it spans decades of technology development, trillions of dollars of investment, and solutions to engineering problems that have resisted resolution for generations. But there is a deeper issue that none of these propulsion concepts have yet forced us to confront. Every calculation presented so far has treated velocity as a straightforward quantity, double the speed, halve the travel time, simple arithmetic. This works perfectly well up to a few percent of light speed, where Newtonian mechanics remains an excellent approximation. But as the desired velocity climbs toward 10, 20, 50% of light speed, the universe begins to enforce a different set of rules. Mass is no longer constant, time is no longer uniform, energy no longer scales with the simple square of velocity. The physics of motion at high fractions of light speed is governed by special relativity, and special relativity imposes costs that make every engineering challenge discussed so far look like a warm-up exercise. The faster you push, the harder the universe pushes back. And at the speeds required to cross 1 light year in months rather than years, that pushback approaches infinity. Every propulsion concept discussed in this journey, from chemical rockets to laser-driven sails to hypothetical antimatter engines, has been analysed using a simplifying assumption that the universe quietly tolerates at low velocities but violently rejects at high ones. That assumption is Newtonian mechanics, the idea that mass is fixed, time flows at a constant rate for everyone, and kinetic energy scales neatly with the square of velocity. These approximations work flawlessly for everything humanity has ever built. Airplanes, automobiles, satellites, interplanetary probes, all of them operate in a velocity regime where Isaac Newton's 300-year-old equations describe reality with exquisite precision. But as velocity climbs toward a meaningful fraction of the speed of light, 10%, 20%, 50%, the Newtonian framework begins to crack, and above those thresholds, it shatters entirely. What replaces it is special relativity, the framework Albert Einstein published in 1905, built on 2 postulates that the laws of physics are identical for all observers moving at constant velocities relative to one another, and that the speed of light in a vacuum is the same for all observers, regardless of their motion. Special relativity produces consequences so counterintuitive that even professional physicists sometimes pause to reconsider them. Time slows down, lengths contract, mass, or more precisely the resistance of an object to further acceleration, increases without limit as velocity approaches light speed, and the energy required to push a massive object to ever higher fractions of light speed does not merely grow, it explodes, rising along a curve that bends toward infinity. This is not abstract theory. It is confirmed experimental fact. Particle accelerators around the world routinely accelerate subatomic particles to 99.9999% of the speed of light. At those velocities, the particles behave exactly as Einstein predicted. Their effective inertia increases by factors of thousands. their internal clocks slow to a crawl relative to laboratory clocks. The energy required to push them incrementally faster climbs toward values that would bankrupt the electrical grids of nations. Every prediction of special relativity has been tested, measured, and verified to extraordinary precision. There is no ambiguity. There is no loophole. The universe operates according to these rules, and any spacecraft attempting to cross 1 light-year at relativistic speed must obey them. The most immediate consequence for interstellar travel is the relativistic increase in effective inertia. In Newtonian mechanics, accelerating a 1 kilogram object by 1 meter per second squared requires exactly 1 newton of force, regardless of how fast the object is already moving. In special relativity, the force required depends on the object's current velocity. The faster it moves, the more force each additional increment of speed demands. The mathematical relationship involves a factor called the Lorentz factor, often represented by the Greek letter gamma. At rest, gamma equals 1. At 50% of light speed, gamma rises to approximately 1.15. At 90%, it reaches approximately 2.29. At 99%, gamma climbs to approximately 7.09. At 99.9%, it hits approximately 22.4, and at 99.99%, gamma exceeds 70. What gamma measures, in practical terms, is how much harder the universe makes it to accelerate an object that is already moving fast. At 90% of light speed, a spacecraft effectively resists acceleration 2.3 times more stubbornly than it did at rest. At 99%, it resists 7 times more. At 99.99%, it resists 70 times more. As velocity approaches the speed of light, gamma approaches infinity. This means the force and therefore the energy required to reach precisely light speed is infinite. Not very large, not technically beyond current engineering, infinite. No finite quantity of energy, delivered over any finite period of time, can accelerate a massive object to the speed of light. This is a structural feature of space-time geometry, not an engineering limitation to be overcome. Now let us translate this into energy requirements for an actual spacecraft. Consider a payload of 1,000 kilograms, a small robotic probe comparable in mass to the Curiosity Mars rover. At rest, this object possesses a rest energy described by Einstein's most famous equation. That rest energy is enormous, approximately 9 times 10 to the 19th joules, but it is locked inside the object's mass and is not directly relevant to propulsion. What matters is the kinetic energy, the additional energy that must be supplied to bring the object from rest to a desired velocity. At 10% of light speed, approximately 30,000 kilometers per second, the kinetic energy of our 1,000 kilogram probe is roughly 4.5 times 10 to the 17th joules. That is 450 petajoules. To put this in human scale terms, the total annual electricity consumption of a large industrialized nation like Germany is approximately 2,000 petajoules. Accelerating a single small probe to 10% of light speed would consume roughly 1/4 of Germany's entire annual electrical output. Every wind turbine, every coal plant, every nuclear reactor, every solar panel in the country running for a year would barely cover the kinetic energy cost of one modest robotic probe. At 20% of light speed, the target velocity for Breakthrough Starshot, though with a payload measured in grams rather than kilograms, the kinetic energy rises to approximately 1.9 times 10 to the 18th joules, roughly 1900 petajoules. This exceeds the annual electricity consumption of a country like France and represents roughly 13% of total United States electricity generation for a single 1-ton probe. At 50% of light speed, the kinetic energy reaches approximately 1.4 times 10 to the 19th joules, 14,000 petajoules. This is approximately 2.4% of total global annual energy consumption, which stands at roughly 580,000 petajoules. For a 1,000 kilogram probe, that fraction sounds almost manageable if you could somehow concentrate years of global energy infrastructure output into a single acceleration event. But 1,000 kilograms is not a crude vessel. It is barely a car. Scale the payload to something that could carry human beings across 1 light year, and the numbers leave the realm of difficult engineering and enter the realm of civilizational impossibility. A minimal crewed interstellar spacecraft carrying even a small team of 4 to 6 people, with life support systems, radiation shielding, food stores, water recycling, medical supplies, communication equipment, scientific instruments, and structural mass would require a vehicle massing at minimum tens of millions of kilograms, and more realistically, 1 billion kilograms or more, roughly 1 million metric tons. At 50% of light speed, a 1 million kilogram vessel demands roughly 1.4 times 10 to the 22nd joules of kinetic energy. That is 14 million exajoules, approximately 24,000 times the total annual energy production of the entire human species. Every power plant, every engine, every battery, every calorie burned by every human body on Earth, all running for 24,000 years to push one modestly sized spacecraft to half the speed of light. And the numbers get dramatically worse as you push higher. At 90% of light speed, the Lorentz factor inflates the kinetic energy to approximately 1.2 times 10 to the 26th joules for the same billion kilogram ship. That exceeds 200,000 years of current global energy production. At 99%, the kinetic energy swells to approximately 5.5 times 10 to the 26th joules, approaching 1 million years of global energy output for a single ship on a single one-way journey. These are not the numbers of a difficult engineering project. These are the numbers of a civilization-scale energy commitment that makes every infrastructure project in human history look like a rounding error. And remember, these calculations assume perfect efficiency. Every joule produced is converted directly into spacecraft kinetic energy. No waste heat, no exhaust losses, no inefficiencies in the beam, the reactor, the magnetic nozzle, or any other component. Real propulsion systems waste enormous fractions of their input energy. Chemical rockets convert less than 1% of their fuel's chemical energy into payload kinetic energy. Even the most optimistic fusion drive designs achieve perhaps 30 to 50% efficiency. Accounting for realistic inefficiencies multiplies every number above by factors of 2 to 100, depending on the propulsion architecture. Deceleration, whose impossibility haunted every propulsion concept in the previous section, takes on a new dimension at relativistic speeds. The energy cost of slowing down from 50% of light speed to rest is not merely large, it is identical to the energy cost of accelerating to that speed in the first place. The total energy budget for a mission that must stop at its destination doubles instantly. For a round-trip accelerate, decelerate, re-accelerate homeward, decelerate at Earth, the budget quadruples. 4 complete relativistic velocity changes, each demanding civilization-scale energy investment. The total energy cost of a crude round trip to a point 1 light-year away at 50% of light speed approaches 100,000 years of current global energy production. But relativity does not only impose costs, it also offers a strange and deeply counterintuitive gift: time dilation. At velocities approaching the speed of light, time passes more slowly for the moving observer than for a stationary one. This is not a perceptual illusion or a measurement artifact. It is a physical reality confirmed by decades of experimental evidence. Atomic clocks flown on high-speed aircraft return to Earth running fractionally behind identical clocks that remained on the ground. Muon subatomic particles produced by cosmic rays in the upper atmosphere survive far longer than their rest frame half-life would allow, because their high-speed motion through Earth's frame dilates their internal clocks. Time dilation is real, measurable, and precisely described by the Lorentz factor. For a spacecraft crew, time dilation means that the subjective duration of an interstellar journey is shorter than the duration measured by observers back on Earth. At 10% of light speed, the effect is negligible. Time aboard the ship passes at roughly 99.5% of the Earth rate. The crew barely notices, but as velocity increases, the dilation deepens. At 50% of light speed, shipboard time passes at approximately 86.6% of the Earth rate. A journey that takes 2 years in the Earth frame lasts about 1 year and 8.5 months for the crew. Noticeable, but not transformative. At 90% of light speed, the effect becomes dramatic. Shipboard time flows at only 43.6% of the Earth rate. A 1 light-year crossing that takes roughly 1.11 years in the Earth frame lasts only about 5.8 months for the crew. At 99%, time dilation compresses further. 1 year of Earth time corresponds to roughly 52 days aboard the ship. At 99.9%, the crew would experience only about 16 days for every year that passes on Earth. The implications are staggering. In principle, a crew travelling at 99% of light speed could cross 1 light year in about 7.5 weeks of subjective time. At 99.9%, the crew would experience roughly 16 days for the crossing. The distance has not changed. The vacuum is still 9.46 trillion kilometers wide. But the crew's experience of time has been compressed so severely that the crossing shrinks from an epic voyage to something resembling a transatlantic flight. This is the seductive promise of relativistic travel. If you can go fast enough, time dilation does the rest. Distances that would take decades at lower speeds compress into weeks or months of subjective experience. A crew could depart Earth, cross 1 light year, and arrive feeling as though they had been in transit for barely longer than a vacation. But the seduction collapses under the weight of the energy requirements we just calculated. Time dilation does not reduce the energy cost. It only changes the subjective experience of a journey that still demands physically real, objectively enormous energy inputs. To reach 99% of light speed requires nearly 1 million years of current global energy production for a single crewed vessel. Time dilation lets the crew experience the journey as a brief interlude. It does not let civilization avoid producing the energy required to make that interlude possible. The universe offers a discount on time. It offers no discount on energy. There is also a social dimension to time dilation that deepens the isolation of interstellar travel in ways no engineering solution can address. A crew departing Earth at 90% of light speed and crossing 1 light year would experience approximately 5.8 months of shipboard time. But on Earth, approximately 1 year and 1 month would pass. The discrepancy is modest for a 1 light year trip at this speed, but for longer journeys, the gap widens dramatically. A crew crossing 10 light years at 90% of light speed would experience about 4.8 years of shipboard time, while roughly 11.1 years passed on Earth. At 99% of light speed over the same distance, the crew would experience about 1.4 years while 10.1 years elapsed at home. The travellers return younger than their contemporaries. Friends and colleagues who stayed behind have aged more. Children born after the crew departed might be adolescents or adults by the time the travellers return. At sufficiently high velocities and distances, the temporal gap becomes generational. A crew member departing at age 30 and travelling at 99.5% of light speed for 50 light years would return having aged roughly 5 years, arriving home at a subjective age of 35. On Earth, approximately 50 years would have passed. Everyone the traveller knew would be elderly or dead. Imagine that astronaut stepping off the ship. She looks the same as the day she left 35, healthy, sharp. The mission control building she departed from has been demolished and replaced. The neighbourhood around the launch facility has changed beyond recognition. The language people speak has drifted not unintelligibly, but enough that she catches unfamiliar slang, unfamiliar cadences, references to events and cultural moments she never witnessed. She asks about her colleagues. Some have retired, some have died. The project director who shook her hand at departure passed away 15 years ago. Her sister, who was 27 when she left, is now 77. They embrace, but the astronaut is looking at an elderly woman she last saw as a young adult. Her niece, who was 3 years old at launch, A toddler waving from behind a security barrier is now a 53-year-old engineer with children of her own. Children the astronaut has never met. Every personal connection has been stretched across a temporal gulf that no communication technology can bridge. She did not leave Earth. She left her time. This is not a distant abstraction. It is the unavoidable mathematical consequence of relativistic travel applied to human relationships. Time dilation does not merely slow the traveller's clock. It severs them from their own historical moment. The traveller departs from one version of civilization and returns to another, carrying memories of a world that no longer exists except in archives. The psychological toll of this displacement, the grief of returning to a world that has moved on without you, has no precedent in human experience. Explorers in previous centuries returned to find their homes changed, but they had aged alongside those changes. The relativistic traveller has not aged. They are a living anachronism, a person displaced not through space but through time, and the displacement is permanent. There is no going back to the era they left. It is gone. Time dilation took it. This temporal exile is not a flaw in the design of relativistic travel. It is a feature of space-time itself. The faster you move through space, the slower you move through time. The universe enforces this trade-off with absolute mathematical precision. And for any species that dreams of crossing light years at relativistic speeds, the cost is measured not only in energy, but in human connection. Every interstellar journey severs the travellers from their past. Every return is a homecoming to a foreign country. The stars are reachable in principle, but reaching them means leaving behind everything and everyone you know, not in the sense of geographic distance, but in the sense of temporal displacement from which there is no return. Beyond the energy and time dilation challenges, relativistic velocities introduce physical hazards that do not exist at lower speeds. The interstellar medium, which already threatened Starshot's gossamer sail at 20% of light speed, becomes an entirely different beast at 90%. Each hydrogen atom now carries roughly 1.2 billion electron volts of kinetic energy, 60 times more than at Starshot velocities, and well into the range of particles produced by full-scale research accelerators. But the problem is no longer erosion of a delicate sail. At these speeds, the cumulative flux of hydrogen impacts generates a forward-directed radiation field intense enough to deliver lethal doses to unshielded biological tissue within hours. Protecting a crew requires meters of dense shielding material at the spacecraft's bow barriers, massing tens of thousands of kilograms that add directly to the vehicle's total mass, and therefore to the energy required to reach relativistic speed. Interstellar dust grains, already dangerous at 20% of light speed as we saw with Starshot, become catastrophic at 90%. The kinetic energy of each impact scales with the square of velocity, meaning a grain that was merely threatening at Starshot speeds now strikes with 20 times more energy. A microgram speck hits with the force of 28 kilograms of TNT. A milligram grain, still invisible to the naked eye, detonates against the hull with the energy of 28 metric tons of TNT. Shielding a crewed vessel against this bombardment requires ablative armor layers of dense material designed to erode gradually under sustained impacts. But that armor adds mass. Added mass demands more energy to accelerate. More energy means larger propulsion systems, which add more mass. The dust grain problem feeds directly into the exponential energy spiral that defines relativistic travel. Thermal management at relativistic speeds presents its own crisis. No propulsion system is perfectly efficient. Energy that does not become spacecraft kinetic energy becomes waste heat. At the power levels required for relativistic acceleration, exajoules delivered over months or years, the waste heat generated by even a modestly inefficient engine would melt any known structural material within hours. Radiating this heat into space requires enormous radiator surfaces, which add mass, which increases the energy required to accelerate, which generates more waste heat. The thermal management problem scales viciously with velocity. At 10% of light speed, it is a serious engineering challenge. At 50%, it threatens to become the dominant constraint on vehicle design. At 90%, it may be physically unresolvable without materials science breakthroughs that have no current theoretical basis. And yet after all these obstacles, after the exponential energy costs, the time dilation paradoxes, the particle bombardment, the dust erosion, the thermal catastrophes, we are still discussing a distance of only 1 light year. The nearest star system to our Sun sits over 4 times farther. The habitable zone planets that generate the most excitement among astronomers lie tens or hundreds of light years away. The opposite side of our own galaxy is 100,000 light years distant. Each of these distances multiplies every challenge discussed in this video by the corresponding factor. If 1 light year demands 1,000,000 years of global energy production for a crude relativistic crossing, then 10 light years demand 10 million, 100 demand 100 million, 1,000 demand 1,000,000,000. The arithmetic is simple, the implications are staggering. 1 light year is not a destination, it is a threshold test. It is the minimum distance that separates dreaming about the stars from actually reaching them. And passing that test requires energy systems, materials, propulsion technologies, and societal commitments that do not merely exceed current human capability, they exceed it by factors of thousands to millions. This is the central revelation that 1 light-year forces upon any honest analysis of interstellar travel. The barrier is not ingenuity. Humans are extraordinarily clever. We have split atoms, decoded genomes, sent robots to the outer planets, and detected gravitational waves from colliding black holes 1 billion light-years away. The barrier is energy. The speed of light is woven into the geometry of space-time, and that geometry imposes a toll on anything with mass that attempts to approach it. The toll is not negotiable. It is not subject to clever workarounds or breakthrough technologies that circumvent it. It is a direct consequence of the structure of the universe, and the toll for crossing even 1 light-year, the very first interstellar distance, the entry-level unit of the void, is measured in quantities of energy that no single planet has ever produced. This does not mean interstellar travel is impossible. It means it is not a problem that a single generation, a single nation, or perhaps even a single century of effort can solve. It belongs to a category of challenges that require civilizational transformation, not merely bigger rockets or better lasers, but fundamentally new relationships between a species and the energy sources available to it. In 1964, the Soviet astronomer Nikolai Kardashev proposed a framework for classifying civilizations based on the total amount of energy they command. The scale was not about intelligence, culture, or moral development. It was about raw power, the ability to harness and direct energy at increasing scales of magnitude. Kardashev defined 3 types. A Type 1 civilization controls and utilizes the total energy resources available on its home planet. For a world like Earth, this means harnessing every watt of solar energy that strikes the surface, every joule of geothermal heat rising from the core, every erg of tidal energy, wind energy, and chemical energy the biosphere produces. The total power available to a Type 1 civilization on an Earth-like world is approximately 10 to the 17th watts, roughly 10,000 times humanity's current total power consumption. A Type 2 civilization controls the total energy output of its parent star. For a Sun-like star, this means capturing approximately 3.8 times 10 to the 26 watts, roughly 2 billion times the power available to a Type 1 civilization. The concept most commonly associated with this level is the Dyson sphere, or Dyson swarm, a megastructure or constellation of collectors surrounding the star, intercepting most or all of its radiated energy. A Type 2 civilization does not merely use energy. It architects its stellar neighborhood to maximize energy capture. A Type 3 civilization commands the energy output of an entire galaxy, approximately 10 to the 36th watts for a galaxy like the Milky Way. This level implies the ability to coordinate energy infrastructure across hundreds of billions of star systems spanning 100,000 light-years. It is so far beyond current human capability that it borders on the theological. Humanity currently sits at approximately type 0.7 on the Kardashev scale. We harness a meaningful fraction of our planet's energy resources, but fall far short of capturing the total. We have not begun to exploit the sun's full output, let alone the energy of other stars. Our entire energy infrastructure, every fossil fuel plant, every nuclear reactor, every hydroelectric dam, every solar farm, every wind turbine on Earth produces roughly 1.8 times 10 to the 13th watts. That is roughly 1/10,000th of the power available to a fully realized Type 1 civilization, and roughly 1/20 trillionth of a Type 2. Now map the Kardashev scale onto the energy requirements of crossing 1 light year. Accelerating a crewed vessel to 50% of light speed requires approximately 24,000 years of current global energy production. A Type 1 civilization, commanding 10,000 times more energy than present humanity, could produce that energy in approximately 2.4 years. Still a massive commitment, but conceivable within a single political administration. A Type 2 civilization, commanding the full output of its star, could produce the same energy in roughly a fraction of a second. For a star-harnessing civilization, launching an interstellar mission would be energetically trivial, comparable to a modern nation launching a weather satellite. The energy required to send a crewed vessel across 1 light year at relativistic speed falls squarely in the transition zone between Type 1 and Type 2. It demands energy budgets that a planet-bound civilization cannot realistically provide, but that a star-harnessing civilization could manage comfortably. 1 light year, then, is not merely a unit of distance, it is a civilizational filter. It separates species that have learned to exploit the energy of their immediate planetary surroundings from species that have learned to exploit the energy of their star. On one side of that filter sits every civilization that has ever looked at the night sky and wondered. On the other side sits every civilization that has actually crossed the void between stars. The filter is not made of distance, it is made of energy, and the amount of energy required is not arbitrary. It is encoded in the geometry of space-time itself, written into the fabric of reality by the relationship between mass, velocity, and the speed of light. Any species, anywhere in the cosmos, regardless of biology, intelligence, or culture, faces the identical filter when attempting to cross the identical distance. The physics does not care who you are, it only asks what you can do. If alien civilizations exist and have crossed light years of space, they solved energy problems that our civilization has not yet learned to formulate, let alone answer. They harnessed power sources that would make our entire global energy infrastructure look like a child's first battery experiment. They built propulsion systems that drew on stellar or even galactic energy reserves. And they did all of this not because they were smarter than us in some abstract sense, but because they climbed the Kardashev ladder far enough to command the energy that space-time demands as the price of admission to the interstellar community. This perspective reframes the Fermi paradox, the famous question of why, in a galaxy containing hundreds of billions of stars, we have never detected evidence of alien civilizations. Perhaps the answer is not that intelligent life is rare. Perhaps intelligent life is common, but the Kardashev filter is brutal. Most civilizations never make the transition from Type 0 to Type 1. They exhaust their planet's easily accessible energy resources, destabilize their climate, fragment politically, and either collapse or settle into a steady state that never generates the surplus energy required for interstellar ambition. Think about what the filter actually requires. It is not enough to be intelligent. Dolphins are intelligent. Crows are intelligent. Intelligence alone does not build particle accelerators or launch spacecraft. It is not enough to have technology. Humanity has had technology for millennia. Fire, metallurgy, agriculture, printing without approaching the energy levels required for interstellar travel. It is not even enough to have advanced science. We have understood special relativity for over a century. We have known the energy costs of relativistic travel for decades. Knowing the price and being able to pay it are entirely different things. What the filter demands is something rarer and more fragile than intelligence or knowledge. It demands sustained civilizational coordination over timescales that dwarf any project humanity has ever completed. Building the energy infrastructure for interstellar travel, whether it takes the form of planetary-scale fusion grids, orbital solar collection arrays, or the first components of a Dyson swarm, requires centuries of continuous directed effort. It requires political and economic systems stable enough to maintain trillion-dollar investments across multiple generations. It requires a species capable of thinking beyond the next election cycle, beyond the next quarterly earnings report, beyond the next decade, and committing resources to goals that the generation making the investment will never live to see completed. This is where the filter bites hardest, not in the physics. The physics is clear and solvable given sufficient energy. The filter bites in the sociology. Can a species of evolved primates, hardwired by natural selection for short-term thinking, tribal competition, and immediate resource acquisition, sustain the kind of multi-generational collective effort that the light year demands? Can we cooperate at the scale of a civilization for the duration of centuries? History offers few encouraging precedents. The longest-running human institutions, certain religious organizations, a handful of universities span roughly a millennium. The light year filter may require cooperation lasting 10 times longer. The light year filter does not require a dramatic extinction event to block a civilization. It does not need an asteroid impact, a nuclear war, or a pandemic. It only requires that the civilization never musters the collective will to build the energy infrastructure needed to cross it. A civilization that fragments, stagnates, or simply turns its attention inward, choosing comfort over ambition, consumption over investment, the immediate over the transcendent, will never cross the filter. Not because it was destroyed, but because it chose not to climb. The stars will remain visible in its night sky, beautiful and unreachable, for as long as the civilization endures. And eventually the civilization will end as all things end, without ever having sent so much as a single gram of matter across the void that separates one star from the next. This is what one light year reveals about us. Not just our technological limitations, but our civilizational ones. The distance is a mirror. It reflects back the question of whether humanity, as a collective species, possesses the capacity for the kind of sustained, coordinated, multi-generational effort that the universe requires as the entry fee for interstellar travel. We do not yet know the answer. We have never been tested at this scale. Every great achievement in human history, the pyramids, the cathedrals, the moon landings, was completed within a few decades by a fraction of the species. The light year demands something qualitatively different. It demands that we become something we have never been, a species that acts as one, across centuries, toward a goal that transcends any single lifetime. 9.46 trillion kilometers, 63,000 astronomical units. 1 year of photon flight. A distance so modest that astronomers barely acknowledge it, yet so demanding that it would require the total reinvention of human energy infrastructure to cross in a single lifetime. Every propulsion technology humanity currently possesses falls short by orders of magnitude. Every advanced concept that might close the gap requires engineering breakthroughs that have resisted generations of effort. And the fundamental physics of relativity ensures that no shortcut exists, that every kilogram sent across that void must pay the energy toll that space-time demands. We began this journey by asking a simple question: how long would it really take to travel 1 light year? The honest answer is that it depends entirely on what kind of civilization is asking. For humanity as it exists today, the answer is thousands of years, using the fastest vehicles we have ever built. For a civilization that has mastered nuclear pulse propulsion, the answer drops to decades. For a civilization with working fusion drives, perhaps a single decade. For a civilization that can build 100-gigawatt laser arrays, 5 years for a gram-scale probe. For a civilization that commands energy at stellar scales, perhaps months or weeks of subjective time aboard a relativistic vessel. Each of these answers is correct for its respective level of technological development, and each one is separated from the next by revolutions in energy production, materials, science, an engineering capability that may take generations or centuries to achieve. The light year does not care which answer you prefer. It sits there in the void. 9.46 trillion kilometers of silence, waiting with infinite patience for any civilization bold enough and powerful enough to attempt the crossing. 1 light year. Just one. The smallest rung on the cosmic ladder. And already it asks of us everything we have, and more than we have yet imagined. That is not a reason for despair. It is a measure of how far we have yet to climb. And the fact that we can calculate the cost, that we can identify the obstacles, that we can articulate with precision exactly what the universe demands, that itself is remarkable. We are a species that has existed for roughly 300,000 years, developed science for barely 4 centuries, and built rockets for less than 1 century. In that sliver of cosmic time, we have mapped the obstacle, we have named the wall, we have measured its height down to the last decimal place. We have not climbed it, not yet, but knowing the height of the wall is how every climb in the history of our species has begun. The ancestors who first crossed oceans did not know what lay on the other side. They only knew the size of the water. The engineers who first split the atom did not know what the energy would be used for. They only knew the energy was there. And now we know, with mathematical certainty, what 1 light year costs. We know the energy. We know the physics. We know the materials challenges, the propulsion limits, the relativistic penalties, and the civilizational thresholds that must be crossed before the crossing itself becomes possible. 1 light year is the entrance exam for a starfaring species. It does not ask whether you are clever. It does not ask whether you are motivated. It does not care about your politics, your biology, or your history. It asks only one question. Can you command enough energy to move meaningful mass across 9.46 trillion kilometers of vacuum in a time frame that matters to your species? Humanity's answer today is no. Not yet. Perhaps not for centuries, but the question is now visible, written in the language of physics and carved into the structure of space-time. And visible questions, throughout the entire arc of human history, have a stubborn, beautiful way of eventually receiving answers. The abyss is only 1 light year wide, and we are only just beginning.